This is section 6.7, Formula and Applications of Rational Equations. In the last section in 6.6, I told you that the most important chapter in any college algebra text, I should say the most important section in any chapter of a college algebra textbook is where you're actually learning how to solve equations with these new types of expressions that we've learned to deal with. Well, if that's the most important thing, then a very close second is actually being able to solve real-world problems with those types of expressions. That is, actually being able to set up the equation that will model some problem in the real world. I mean, the whole purpose of college algebra in general, is to find some missing value. That is, you are going to be able, through this section, to set up the relationship between some actual quantities representing real-world things. And once you establish what their relationships are, you're going to have only so much information, and you're going to be trying to find what's that missing piece. What's the thing that I don't know? Well, if the equations that you end up with, the equations that model the relationships between the variables in the problem, turn out to be rational equations, then we need a technique for solving those. And in fact, that's what we covered in section 6.6. Now that we have the technique, let's look at some actual problems where that type of equation shows up. The first thing we want to do is talk about a little bit of work that we can do with formulas. Now, you've seen a number of application problems show up where the word problem gives you a formula for some model. That is, some scenario where the quantities in the problem are modeled by this particular formula. In the case where those things are rational functions involved in that formula, one of the things we want to be able to do is solve the formula for another variable. Right? The reason why you might want to be able to do that is, imagine that you have a particular formula like this 1 over p plus 1 over q plus 1 over f. We'll talk about in a second what exactly that means, but in that case, imagine that you were given a set of numbers like p and q and you wanted to find f. Now you got two options. Your first option is to plug in the p, plug in the q, then find f. Okay? Which makes sense, that's reasonable. What if you had like a dozen p's and q's and you wanted to find the f for all of those? Well, you could do that every single time. That is, plug in the p, plug in the q, solve for f. Plug in the p, plug in the q, solve for f. What if we simplified that process by first solving the formula for f? And then all we got to do is we have a new formula where f is equal to something that depends on p's and q's. Just plugging in the p's and q's, we don't have any solving left to do. We can do all the solving in one step. So being able to rearrange formulas so that you've solved for the variable that you're going to most commonly want to be hunting for, that's a useful tool. So that's what we're going to be talking about here. So in Roman numeral 1 of section 6.7, we're talking about the steps to solving a variable, or solving for a variable in a formula containing a rational expression. What you're going to do is you're going to use the LCD in the same way that we used LCDs to solve equations that had only one variable. If they're multiple variables, same strategy. Find the LCD, use that to eliminate the fractions, and then get the desired variable by itself. That is, isolate the desired variable. So let's take a look at this example that we see right here. The example you see here comes from a field of study called optics, which is generally taught as part of a physics course, but I'm just going to show you the formula without having to worry too much about where it comes from or why it's true. Here's what the formula represents. It is p is the distance of the object from a lens or a mirror. So imagine you have some lens here, and you've got some object. Say this is me right here. And then my image is traveling to this lens, and the lens refracts my image, and then it becomes in focus on some wall over here. You see me showing up on this screen. There's my picture, right? That's coming through that lens. Okay. The p is the distance that I am from the object, or sorry, that the object is, being me in this case, is from the lens. So that's p. The distance that my image shows up from that is also is q in this case. And then the focal length, that is the distance between the lens itself and where that focal point is called f. Okay? So here's what we know. 1 over p plus 1 over q is equal to f. We want to solve this thing for f. So start by finding the LCD. The LCD in this case is going to contain every factor that appears in the denominator, so P, Q, and F. And then you're going to multiply through by the LCD. I'm going to take 1 over P plus 1 over Q and 1 over F and just multiply both sides by P, Q, and F. P, Q, and F. So distribute this to each one. Multiply it on the right hand side as well. When I take PQF times 1 over P, the P's cancel. I'm left with QF. When I take PQF times 1 over Q, the Q's cancel. I'm left with PF. And on the right hand side, when I multiply that, the F's cancel. And I'm left with PQ. Now in order to try to get the F by itself, notice I have two terms with the F in them, but because they both have an F, I am able to factor out that common F from each one. Now recognize that the operation connecting F to the rest of this side is a multiply, so if I divide both sides by Q plus P, they will cancel out of the left hand side, and I have that F is always equal to PQ over Q plus P. And that's what we're looking for here. We now have solved that formula for F. Now we're going to start taking a look at several of the types of problems that we will set up the equation for. That equation will turn out to be a rational equation. I think we're going to look at three of them. We're going to look at work problems, we're going to look at motion problems, and we're going to look at number problems, very simple number problems where we state something, some property that numbers have. Let's start with the combined work problem. Now, this is a good kind of managerial type example where you've got two objects. Actually, you could do two or more objects, but they're working together to complete a common task. Say, for example, my wife and I are painting the room, and we're going to establish what's the relationship between how fast I work and how fast she works, and how fast it would take us, or how long it would take us to work together to complete the room. So say, for example, it takes me 3 hours to paint the room. It takes her 2 hours to paint the same room. If we work together, assuming that we don't, distract each other, but we're both working at the same pace as we did when we were alone, how long would it take us? Me 3 hours, her 2 hours. How long will it take us working together? Okay, if you think about that for a while, you might come up with numbers like, the average of the two, like 2.5 hours. But that doesn't make a lot of sense, because it should take less time than it took her by herself. So it's going to be less than 2 hours. I'm going to help her out at least a little bit. Right? So how do we figure out how much time it's going to take us working together to do this? So these work problems are of that nature. So consider two objects working together to complete or to finish one complete task. Okay, well, basically think of it this way. We're going to take how much is done, that is the part done by the first person, and we can actually generalize this and start talking about objects too, like two printers working together to print a batch of brochures or something. But it's going to be done by the first person or first object. Okay, second, it's going to be the part done by the second person. Okay, we want the part, that is the fraction or percentage, however you want to think of it, done by the first person plus the fraction or percentage done by the second person needs to equal one complete job. Right? So how do we calculate how much is done, what fraction is done by each person? So we're going to use the formula that the part of the job done is going to be equal to how fast they work, right? How much of the room I paint for every hour that goes by. It's like my miles per hour. It's my room per hour. How much of the room per hour do I paint? Times how long I actually paint. So rate, again, means how much work is complete per unit of time. And here's the general rule. Think of it this way. If I can paint the room in 3 hours, okay, that means I can do 1/3 of the room per hour, doesn't it? That's how much of the job I get done in 1 hour. If I can paint the whole thing in 3 hours, I can do 1/3 of the room every hour that goes by. Let's just make the assumption I'm working at a nice constant rate. I've said that once already. So, in general, if a person needs to complete the task in X units of time, their rate is always going to be 1 over X. So if it was 10 hours it took them, their rate is 1/10 of the job per hour. Okay? Now let me give you a little bit of a strategy here. I'm gonna show you as we scroll down here to the next part of the page that whenever you've got a combined work problem, one of the best things you can do is organize the information given to you into a table so you know what's what. You know what information you've been giving and then how to put together that information into an equation. Here's what the table is going to look like. We're going to have on our table 2 rows. Okay? So I'm making use of my drawing utensil here to get the 3 rows nice and straight. Okay, actually 2 rows here, and then we're going to have person 1 or thing 1, object 1, whatever's doing the first part of the job, and person 2, whatever's working on the second one. All right, now we're going to have 3 columns. Whoop, that wasn't straight at all. Let's try that again. There's 1. There's 1. Let's try that again. Sorry, you could have this drawn before I started recording, but either way, you get the idea. All right, so the first column is rate. That's from this formula that we've got right here. Okay, that's what's going to go in this column. So if we're given the information, like we're actually given a time, how long it takes person 1, we'll put 1 over their time. If we don't know that, we'll let that be our variable. We'll do 1 over the variable x. Okay, then we're going to have a column for time together, how much time they spent working together. And then the last column is going to be the part of the job done. Now remember, from before, the part of the job done, and I'll even scroll up so you can take a peek at it, the part of the job done is rate times time. That means rate for the first person, which is going to be right here, times time, how long they work, is going to equal, so to get the last column, you just multiply the first 2 columns together, and you do that on each row. Okay? Then what you do is you add up the last column and set it equal to 1. By doing that, you'll then have your equation. Because, like I said, the part done by first person plus the part done by the second person needs to equal 1 complete job. Now we use our strategy on this example. Tom can plant a tray of flowers in 15 minutes. Frank can plant the same tray in 25 minutes. How long will it take them working together to plant the tray of flowers? We know it's going to be something less than 15 minutes because it's got to be better than what Tom can do by himself. We recognize that it's a work problem. I mean, you almost always will see these types of words show up, so you know this is the strategy that we're going to apply. Start by identifying your rows. That is, who are the people, what are the different parts working together. We have Tom and we have Frank. Okay. Boom, 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 boom. So, rate. How fast does Tom work? Not how long does it take Tom, but how fast does he work? Well, our units of measure are in minutes, but it's 15 minutes that it takes him for the whole job, so his rate is 1 over 15. He will get 1/15 of the tray planted every minute. Frank's would be 1 over 25 because he gets 1/25 of the tray planted every minute. Now, how long do they work together? Well, the answer is we don't know, right? How long will it take them to work together? That's the question. So we're going to put the variable here, and it's going to be the same. Now, for all combined work problems, this cell in your table and this cell in your table are always going to have the same value in them. Now, how do we get the last column or the part of the job done? Yeah, the fraction done by Tom is how fast he works times how long he works. X times 1 over 15 is X over 15. X times 1 over 25 is X over 25. And now last of all, we know that the total job done, that is, if we add what part is done by Tom and what part is done by Frank, we will get one complete job. So that's our equation. Right? Okay. So X over 15 plus X over 25 is equal to 1. To solve that, we have to find our LCD, which the LCD of 15 and 25 is 75. So I multiply both sides here by 75. So I'll have 75 times X over 15 plus 75 times X over 25 is equal to 75. 5 goes into 75 5 times. 25 goes into 75 3 times. 5x plus 3x is equal to 75. Combining like terms on the left hand side gives me 8x equals 75. Divide both sides by 8. And x is equal to, plug that into my calculator, I get 9.4. So it takes 9.4 minutes together. Which is consistent with what we expected. It's less than 15 minutes, but we now have a pretty accurate assessment of how long it will take them working together. Moving on to the next example, we're looking at Chris Burdett and Mark Greenlaw, who work at a vineyard in California. When Chris and Mark work together, they can check all the plants in a given field in 30 minutes. When Chris checks the plants by himself, it takes him 45 minutes. How long does it take Mark to check the plants by himself? So imagine you're the manager for these two guys, and you've seen that this particular vineyard, when they check the plants, it takes them 30 minutes together. You've also had the scenario where Chris has had to do it by himself. Now, for whatever reason, Chris has called in sick and Mark needs to check the field by himself. And you're going to assign him other tasks during the day. You as a manager want to know, okay, can I figure out how long it's going to take Mark to get this job done? And if I can do that, then I can plan, appropriately. I can manage the time as needed. Well, we now have a strategy for doing that. We look at Chris and we look at Mark and we ask, okay, so what's their rate? How fast do they work? Again, Chris, we know, can do it in 45 minutes, so 1 over 45 is his rate. Now what about Mark? That we don't know. We don't know how fast Mark works, so we're going to have to put that as our variable. Still, because it's the rate and we're trying to find how long it takes him to work, we're going to use 1 over x, 1 over his total time. Okay, so x is the time it takes Mark. It's always a good habit to identify what your variable that you're using represents, if you haven't made that clear before. Time together. Now we know this one. Time together is 30 minutes. And that's always going to be the same on both rows. And then the part done will be 1/45 times 30. So 30 over 45. Or I can reduce that. Take a 5 out of the top and bottom. Actually, I can take 15 out of the top and bottom and get 2/3. The time together, 30 times 1 over x, is going to be 30 over x. So we're going to add these together. 2/3 plus 30 over x is equal to 1 complete job. That's our equation that models this problem under, again, the assumption that they're working at nice constant rates. Now find the LCD, which clearly in this case is 3 times x, and let's multiply through by 3x. Distributing this to each term in the equation. 2/3 times 3x is going to give me 2x plus the x's cancel plus 90 is equal to 3x. So to solve for x, all I got to do is say subtract 2x from both sides. I get x is equal to 90. So it takes Mark 90 minutes by himself. Okay? There we go. All right, let's take a look at the next type of problem. The next type of problem that you're going to be asked to handle are basic number problems. And all I mean by a number problem is you're given some statement about the relationship of numbers and you want to set up the equation. We're basically translating English statements about mathematics into a mathematical form. For example, you see one number is twice another. That's where we understand that one number would be x and twice that number. That is, if this number is twice another, if that one's x, I should say it this way. If this one's x, then twice that number would be 2x, right? Sum means plus, but this is the one word that I want to emphasize in this section because it's where the fractions show up, and we're talking all about rational expressions in this chapter. You just got to remember the word reciprocal means basically to flip the fraction, right? 1 over the number, or to flip the fraction. That's equivalent way of thinking of a reciprocal. So the reciprocal of say 2 would be 1/2 of 2/3 is 3/2, etc. Okay. Now, if the reciprocal is of some number x, we would write that as 1 over x. So here's what we've got in identifying the different pieces here. We've got one number is twice another number. We have the sum of their reciprocals. So what's the reciprocal of 2x? According to this rule, it's 1 over the number, so 1 over 2x. Sum means plus, and what's the reciprocal of x? Well, that's 1 over x. And is always means equal sign, right? So is 3/4. Now that's how we just went from some statement in English into a mathematical expression. Now I would find my LCD, which happens to be 4x in this case, right? The lowest common denominator of 2 is 4, and then I need 1x, or an x to the first, because that's the highest power to which it appears. Now multiply through by the 4x. Multiply each term by 4x, we end up with 4x times 2x. The x's cancel, I'm left with 2, because 2 goes into 4 twice, plus the x's cancel again on the second one, so I end up with 4 is equal to, the 4's cancel, I'm left with 3x. So 6 is equal to 3x, divide both sides by 3, we get x is equal to 2. Now be careful here. It asks for the numbers, plural. So what are the numbers? Well, this was one number, the other number was twice it, right? So the numbers are 2 and 4 because the other number was twice it, right? You could just stick the 2 into 2x and you get 4. Okay, so that's what I mean by solving a number problem. Now let's take a look at the last type of word problem that we're going to be doing in this section. What are so-called motion problems? These poor problems get such a bad rap from the world at large. These are the type of problems where we're talking about a car traveling against the wind and another car traveling with the wind, and they leave city A and travel to city B, and you got to try to figure out how long it's going to take them to get there, when they'll meet, that kind of stuff. And the reason they get such a bad rap is that if you look at it without any kind of algebraic background whatsoever, there's a lot of information being thrown at you in a very small amount of time, in a very tiny window of a paragraph, and it's all complicated and it's messy, and you're like, I don't know, my head hurts, I can't explain what's going on. But the whole purpose of a class like this is to say, okay, I understand that that's a lot of information to process, but algebra is all about organizing that information. And here's what I'm going to do. I want to provide to you a strategy for handling those types of problems. A way to organize, if you will, the relationships between these quantities. Now, we all know the basic relationship between distance, rate, and time. It's pretty common. A lot of you will have seen distance is equal to rate times time in the form where the distance is by itself on one side. You could easily solve that for time or rate. But that basically says that if I'm traveling 60 miles an hour for 3 hours, I'm going to multiply the 60 times the 3, right, to get how far I actually go. Now, if you turn that on its head and you want to say, okay, I know I'm traveling, I got my speedometer set on 71 miles an hour on the highway. Yeah, that 1 mile an hour, probably over the speed limit, but let's say that's what you got. And you know that you have still 175 miles to go till you get there. And you're always, I'm doing this when I'm driving down the road on a long road trip. How much longer is it going to take me to get there? Well, to find that, all you got to do is divide how far by how fast. That just comes from taking this formula and dividing both sides by r, right? R, you get that time is distance over rate. The r's cancel here, you get distance over rate. That's how you figure that out. Now, with that basic formula and with using a similar type of table that we used for combined work, we're going to have all the pieces, all the tools in our mathematical toolbox to answer some of these motion problems. Now here's how I'm going to set this up. I'm going to use a similar table. I'm going to have, a part of my trip. We'll call it part 1 of the trip. We may have part 2 of the trip. In some of these examples, we'll be looking at going uphill one way and downhill the other. We'll be going into the wind and against the wind. We may be rowing a boat going into the current and against the current. But you have these 2 different parts of the trip. You put those as the rows. First thing you want to identify, okay, what's the distance? How far am I traveling for that part of the trip? Second thing, what's the rate? How fast am I going on that part of the trip? And then, for these types of problems, you're almost always going to have, and this is just because this is what we're looking at in this section, we're going to not know what the time is, and so we're going to take and use distance over rate. That is, we're going to be able to find the last column by dividing the first 2 columns. Distance divided by rate will give me the time. And then we're going to use some information in the problem to set up an equation based on that time. Okay? All right, so let's see how that will work. We got a couple of examples on the next page. With a 3 mile per hour current, Frank can row 6 miles in the same amount of time it takes to go 2 miles against the current. Okay, find Frank's speed in still water. So think about this. We've got Frank in the river. Okay, so here's the river. And let's say the current is going this way. Okay? So first thing we know is that if he's going with the current, right, he can go 6 miles in the same amount of time that if he goes against the current, he can go 2 miles. And one thing they tell us is that the current is moving at 3 miles per hour. Okay? Now the question is, what's his speed in still water? Now I want to make a quick note here that we're going to assume, okay, that the speeds are additive. Okay? Now what does that mean? That means that if his speed let's go ahead and write this in red here, so I'm answering the question. With the current or against the current are the 2 parts of this problem. Okay? Now for the distance, you've got those. We've already got them set up here. If he's going with the current, it's 6 miles. If he's going against the current, it's 2 miles. Now what about his rate? Okay? That's where this piece of information comes in. Speeds are additive. That is, if he rows a certain rate in still water and the current is 3 miles per hour and he's going with the current, they add together. Whatever I'm going in still water, or whatever I can do, or Frank can do in still water, plus whatever the current helps him. Now if it's the other direction, if he's going against the current, it's going to subtract. Okay, so his rate is going to be whatever it is in still water, which we don't know. And if he's going with the current, it's plus the current's speed. And if he's going against the current, it's going to be minus the current and its speed. Okay? And so now the time using distance over rate gives me the following, that the amount of time it takes him with current is 6 over x plus 3, right? The distance divided by the rate. Against the current, it's going to be 2 over x minus 3. Now, we don't just add the last column up to 1 like we did with combined work. We actually got to pay attention here. A little bit of critical thinking. What do we know about those times? Well, look at this. What does it say right here? In the same amount of time, which says what? They're equal, right? 6 over x plus 3 is equal to 2 over x minus 3. It's the same amount of time, right? We know their distance, we know the rates, we can calculate their times, and we know those times have to be equal, so this equation must be satisfied by whatever his still speed is. Now that we got an equation, we can solve it using lowest common denominators. The LCD will be x plus 3 times x minus 3. Multiply both sides by that. Once I distribute it on the left, the x plus 3's cancel. I'm left with 6 times x minus 3. On the right, the x minus 3's cancel. I'm left with 2 times x plus 3. Now simplifying both sides, 6x minus 18 must be equal to 2x plus 6. Subtract 2x from both sides. Gives me a 4x. Let's add 18 to both sides. That is 24. Okay. Now divide both sides by 4. 24 divided by 4 is 6. So his speed in still water is 6 miles per hour. Okay? There's your final answer. Sally walks up a hill at 4 miles per hour. Alright, so let's draw our hill. It's got to be green, so here's my hill. Okay? Boonk. We don't care what happens on the other side. So she's going up the hill. Okay, at 4 miles per hour. She goes down the hill at 6 miles per hour. Okay, it takes her 1/3 of an hour longer to go up than it does to go down. The question is, how far up the hill does she go? What's the distance? Okay, well, let's organize our information into a table. What do we got? What two parts have we divided this trip into? Well, we've got the uphill, we have the downhill. So let's look at their distance. Distance will be uphill. Well, actually we don't know, do we? Well, let's stick our variable in there. The distance she travels up the hill will be x. So what's her distance she travels down the hill? Well, I think it's pretty clear from the problem. Let's assume she's going to go the same distance back down. She starts at the bottom of the hill, she walks up it, and then she jogs down. She's going to travel the same distance both ways. Next question. What is the rate? How fast does she go in each direction? Well, that's given to us. Uphill, she goes 4 miles per hour. Downhill, she goes 6. Hey, piece of cake. We're flying right through this one. Okay, what is the time that it takes? Well, that's not so bad either, right? Because it's always distance divided by rate. Distance over rate. So that's x over 4 and x over 6. Alright, now here's where you got to be careful again. You got to say, okay, what do we know about the times? Right? How are these two related? And here's the key. It's not that they're equal now, but we have this. It takes her 1/3 hour longer to walk up the hill than to jog down the hill. So one of these is 1/3 of an hour more. So plus 1/3 is what we mean by 1/3 more. Now, which one do we need to add the 1/3 to? Well, she's going to go down faster, right? We know she's traveling faster here. So the time it takes her to go down is quick, whereas x over 4 is going to be a little bit longer. So it's going to be 1/3 longer than the jog down the hill, right? Anytime you see a phrase like that, the one part of the phrase that it depends upon, the dependent part of that, is going to be where what we do the function to. So we're saying 1/3 more than down the hill, so it's downhill plus 1/3 is equal to uphill. All right, now we just got to solve that. Hey, that's actually a pretty easy one. To solve it, we find the LCD for this particular equation. The LCD is going to be the smallest number that 6, 3, and 4 all go into, so that would be 12 in our case. So we're going to multiply both sides of this by 12, so distribute 12 to each term. You see in the equation you'll have x over 6 times 12 plus 1/3 times 12 is equal to x over 4 times 12. So now we just simplify these expressions. 6 goes into 12 twice, so I'm left with 2x. 3 goes into 12 4 times, so I'm left with plus 4. And 4 goes into 12 3 times, so I'm left with 3x here. Now if I subtract 2x from both sides, 2x from both sides leaves me with 4 is equal to x. 4 equal to x means that that is the solution to the distance problem. So the distance that she went up the hill is 4 miles. And that ends that example. And that's the end of section 6.7.